Welcome to another session on GATE. So in this session, we are going to look at the power system questions that came in GATE 2020 for electrical engineering, right? So there were basically 6 questions for power system, right? 3 of them were fill in the blanks and 3 questions were with options. We look at the topic-wise distribution. There was one question from protection, one question from fault analysis, one question related to Y bus or bus admittance matrix, one question related to load flow analysis, one question from voltage control, and one question from frequency control, right? Let's look at the first question. So if you look at the first question, it is from the protection, right? So what they're saying is that there is a lossless transmission line, right, which has reactance of 0.2 per unit per phase uniformly distributed, right, along the line. So what they have said is X transmission line is 0.2 per unit. And it says that it is connecting a generator bus and a load bus, right? This is the load bus and we have a generating bus, right? And it says that there is a distance relay at the generator bus which protects up to 80% of the transmission line. And they are also saying that there is no generation at the load bus and the voltage at the generation bus is 1 per unit. What they are asking you to find is the threshold per unit current for operation of distance relay for a solid 3-phase to ground fault. Okay, so they are saying they want you to find I threshold, which is basically I fault for the with the X threshold, right? So let's look at how to calculate this. So this is one of those questions that has a lot of information, right? So we need to unpack it properly. So V is given as 1 per unit, X transmission line is given as 0.2 per unit, and the distance relay setting is given as 80%. So if you see the I threshold or the I fault is given as V divided by X threshold. So the question over here is what is X threshold? So if we don't pay attention to the question and we directly use the value of the transmission line, you will get the answer as 5 per unit, right? And if you go back and check the option, there is an option with 5 per unit, but the answer is wrong because they have clearly said that the distance relay setting is 80%. So in this case, the X threshold, right? X threshold would be X transmission line into distance relay setting. So that would be 0.2 into 80% of that is 0.8. So it would be 0.16. And if you calculate with this value, I threshold, it would be 1 divided by 0.16. You will get it as 6.25 per unit, right? And if you look at the options, the correct answer is A, right? Now let's look at the second question. So this question is from load flow analysis. So they're saying that we have a PV bus and they want to know what is the most relevant information for this P. So what is P? P is the actual generation at that bus at that instant, right? So is the rated power output of the generator P? Not necessarily, right? So the rated output power can be P, but it is not always P, right? Then rated voltage uh, is not the correct answer. Base power of the generator uh, is required to calculate the per unit value, and it is not the P. But the solution of economic load dispatch. So what is solution of economic load dispatch? It is how much each generator should produce considering the economic constraints and the system operating constraint. So this would give you PI, and this is what is the closest to the actual generation. This is the closest value that we have to the actual generation at that bus, right? So the correct answer is D. The third question, okay, is from frequency control. So they have said that they have a synchronous generator rated 50 hertz and delivering 100 megawatt, right? And then the load is increased. The generation had to be increased by 110 megawatt by 10 megawatt, which caused the frequency to drop to 49.75 hertz. Now they say that the load increased again and the system frequency became 49.25 hertz. So if we look at P on one side and frequency on other, right? So at first it was 100 and the corresponding frequency was 50. Then the load increased by 10 megawatt. So always the load has to be matched by generation. So the new generation would be 110, right? And the frequency was 49.75. Now the power further increased. Let's say it is X, right? And the frequency became 49.25. So since this is under droop control, it will follow the droop characteristic, right? So if we look at the slope of the droop characteristic, it is given as delta F by delta P. So let's calculate it as F2 minus F1 divided by P2 minus P1. So if you do that, you will get it as 0.25 divided by 10, which is minus 0.25 divided by 10, which is minus 0.025, right? Now we can extend this to find X, right? So let's take this pair. We can take any pair since it's a straight line. Let's look at this pair. So what is delta P? Delta P would be delta F divided by 0.025 minus, right? So X minus 100 would be minus of 49.25 minus 50 divided by 0.025. And if you do this calculation, you will get it as 30. So what is X? X is 100 plus 30, which is 130 megawatt, right? So this question is a fill in the blanks type question. So this would be 130.00 megawatt. Okay. Then the next question is related to the Y bus, right? So what they have said is that you have two transformers, right, with the turns ratio that is provided, and you have to calculate the Y bus for this system, right? So let's consider this node as A and this node as B, right? So if we look at it just from that node point of view, right, it would be VA, VB, and Y, right? So if you look at the Y bus, it would be VA, VB is equal to Y minus Y minus Y, Y, and IA and IB. We can present VA in terms of VI and IA in terms of II, just by considering the turns ratio over here, and similarly VB and IB in terms of VJ and IJ, considering the turns ratio. So it would be VI by TI, VJ divided by TJ is equal to Y minus Y minus Y, Y into II Ti and ij tj, right? So if we separate this and rearrange it, you will get it as vi vj is equal to ti 0 0 tj to y minus y minus y y into ti 0 0 tj into ii ij, right? So this would be multiplied, you will get it as ti square y minus ti tj y minus ti tj y and tj square y, right? So if we look at the option, the correct answer is 2, right? And the next question is from voltage control. So what they have said is that we have a bus 1 with magnitude v1 is 1.1 and is sending reactive power q12, right? So this is 1.1 per unit and it is sending q12, and the voltage over here is 1 per unit under this condition. And they're saying that there is no loss, so that means r is equal to 0 and the angle is 90 degrees. So z is basically x, right? Keeping the voltage at bus 2 is fixed. Okay, so they're saying that voltage, so now they are keeping the voltage at 2 fixed, it's still 1 per unit, but the magnitude of voltage at bus 1 has changed, right? So we don't know what is the value of, let's call it as V under this new condition. And what has happened? Q12 has increased by 20%. So the Q12 new is 1.2 times Q12. And they're saying is the real power flowing under both conditions. So there is no real power flowing, the P is 0. And they are asking us to calculate the magnitude of V1, or in our case, V, right? Let's look at how to solve this problem, right? So since it's under this given condition, we can say Q12 is V1 into V1 minus V2 by X, right? So if we rearrange this, you will get Q12X is basically, if we consider the first condition, right, where V1 is 1.1 and V2 is 1, we will get it as 0.11, 1.1 into 0.1, right? We get it as 0.11. So, and Q12 new, right? What would be Q12 new? It would be V1 into V minus 1 divided by X, right? And what is this? This is, we also know that also, which is equal to 1 point times Q12, right? So this is 1.2 times Q12 is equal to 1.2 times Q12 is equal to V into V minus 1 divided by X. And if you rearrange this, you will get 1.2 times Q12 into X, which is 0.11, right? To 0.11 is equal to V square minus V, or basically we have quadratic equation in our hand, which is V square minus V minus 0.132 is equal to 0. And if we solve this, we will get V as 1.12. So the answer over here is 1.12 And this is the last question. This is the last question. And this question is from fault analysis, right? So what they've said is that they have a cylindrical cylindrical rotor synchronous generator, which has XD. XD is what? Direct axis impedance is 0.7 per unit, and subtransient. What is subtransient reactance? It is 0.2 per unit, right? And they're saying that the terminal voltage at the time of operation is 1 plus J0 per unit, and the internal EMF, right, under normal operation condition is 1 plus J0.7 per unit, right? Now they're saying that three-phase short circuit fault, solid three-phase short circuit fault occurs at the terminal of the generator, and what they are asking for is the magnitude of the subtransient internal EMF, right? So when we are having a solid fault, what is IF? That will be the current at that instant. It would be ET minus V divided by XT, right? So if you substitute the value, you will get it as what 1 plus 0.7 J minus 1 divided by 0.7 J, right? So you will get this as 1 per unit, right? Now they are asking for the EMF under subtransient condition, right? So we should not be using the direct axis impedance here. We should be using the subtransient direct axis impedance or subsynchronous reactance, right? So it's called as EF double dash, right? What would that be? It would be V plus I fault into, so this is that instant of subtransient XD double dash. So this will be 1 plus 1 into J.2. So you will get it as 1 plus J.2, and since they are asking for the magnitude, if you do that, you will get it as 1.09, right? So the answer is 1.09. So those were the questions from power system in the last year. I hope you guys were able to follow the questions. Yeah, and thank you for your time.